It's nice to be here, and it's a pleasure to meet Professor Vavilov a year ago, and the result is that I come to visit. I was thinking about St. Petersburg. I've never been here before, and I remember stories of Gogol, and he said, "Oh, Russians love stories." So I'm going to start with a story. It's personal, so I mean it's not definition theorem proof. So. Okay, so here I am as a child, a mathematical child, and this is in the late 1960s when I was in graduate school, and I took a basic group theory course, and one of the first graduate courses I took, I shouldn't have taken really, but it was by a course of John Thompson on part of the classification of n groups. And let me tell you what an n group is. Is this generally known to you? I'll make the definition. It just takes a minute. Okay. So if G is a finite group, a local subgroup is the normalizer of a non-identity P subgroup. P is a prime number. Okay. And an n group is a non-solvable group. It's a non-solvable finite group in which every local subgroup is solvable. So n means normalizer of a local subgroup. Okay, now there was, when the classification of finite simple groups got started in the early days, the first question, what are the minimal simple groups? It's a simple group in which every proper subgroup is solvable. Okay, well this contains the set of minimal simple groups, but you can use induction more easily with this family, so it makes sense as a strategy. Okay, and then the theorem of Thomson is a list of n groups, which I will not list for you, unless you really want me to. Then I'll try to do it. But this course I took was really a section in the middle of the paper. It's like walking into the middle of a movie. You can guess what's going on, but you're not sure. So one of the intermediate results was a characterization of the groups S4 of 3 and G2 of 3 by some local properties. And this is pretty technical. I won't even try to describe what the properties are, but some internal properties lead you to this group or this group. And this, this is old-fashioned notation for projective special group, dimension 4, and this means over the field of 3 elements. Okay. All right, now I'm a young student. I learned the definition of a group and a few simple things, and I didn't really know what this meant. But when you look at the list of n groups in his theorem, these do not appear. So why are they not n groups? Well, they've got to have some kind of non-solvable local subgroup. And I later learned, okay, I took a course from Roger Carter. It's a great introduction to Chevrolet groups. And I learned the following fact, that PSP43, which is the Chevrolet group C2 of 3, is isomorphic to PSU42. And now what's that? That's twisted A3 of 2. I think that's, do we have common language? Yes? Yes. Okay, good. So this is a if you look at the parabola subgroups in this as a group in characteristic 3, they're all solvable. But here, different viewpoint, that's the root system, and then if you take this parabolic subgroup, it looks like an elementary abelian group of order 2 to the 4th extended by SL24. That is non-solvable. Okay, so that shows that this is not an n group. That explains why it doesn't appear here. Okay, so I learned something. Now, what about G2? Well, it's not isomorphic to something different, so I can't use the same idea. So I learned that I'll take G2 of Q, where Q is an odd prime power, that there exists one conjugacy class of involutions, and for an involution, the centralizer has the form S1, S2, where S1 and S2 are copies of SL2Q. The subgroups commute element-wise, and the intersection has order 2. This is my notation for a cyclic group of order 2. In this context, it's got to be a group, so that's okay. And all you have to do is think about the diagram of type G2. And you take, I'll make dotted lines. Take these two pairs of roots that are orthogonal, take the SL2s associated to them, and you can create a subgroup like this. Okay, so this isn't trivial, but it's fairly standard way to work in Chevrolet groups. So I learned that. Okay, and next, if E is a subgroup of G2 of Q, and E is a 4s group, then E is contained in a split torus. Well, this is a general fact about Chevrolet groups, at least of the simply connected sort. But in G2, it's very concrete. All you have to do is look in this group. You've got one involution in the center. So you seek a second involution, and it's got to be a product of an element of order 4 from this times an element of order 4 from this. And by inspection, it lies in a torus. Okay, so 2-generator abelian 2-group lies, an elementary abelian 2-group lies in a torus. And then the last step, the centralizer of E is that torus. Oop, I didn't give it a name. Call it boldface T. Is T extended by a group of order 2. So this is notation for a group extension. A torus on the bottom, and you go up by index 2. And it's an easy calculation that this is split. So if you take and W in T, I'm sorry, in the centralizer of E, but not in the torus part, then W has order 2. And all such are conjugate. Why are they all conjugate? Because this is an odd order group. A CeLO 2 group of this extension is order 2. And conjugacy part of CeLO theory says this. So we get an extension of this group to U, elementary abelian of order 8. Okay, so here's an elementary abelian group of order 8. It has rank 3, so it cannot be in a torus. I constructed it so that it wasn't in that torus, but it's not in any torus. And the normalizer of U is transitive on flags that look like this. Where this has order 2 and this has order 4, and of course this one has order 8. So it follows that the normalizer of U, mod U, is isomorphic to GL 3,2. Okay, so that's an easy argument. So the normalizer of U is therefore a non-solvable local subgroup in G2 of Q, and in particular for G2 of 3. Okay, so non-solvable. Okay, well, that's my story, why I started thinking about finite subgroups of groups of Lie type, and some of the strange ones that can come up. And I learned about 1974 that there are subgroups that look like this inside F4 over various algebraically closed fields, characteristic not 3. And this is non-toral. And there's a similar one for 5. And what about K? K is characteristic not 5. And there are several other examples. And I learned that Alexeyevsky, or one person with that name at least, found these and several others. I found these myself just playing around. And in 1984, I think it is, with Aryeh Cohen, we started to try to classify.
So this is what Alexievsky called Jordan subgroups or something?
Yes. He did call them Jordan subgroups. I cannot explain why he called them that, but yes, that's the terminology that he used. I just say non-toral. And there are many other examples. I could write down this one. And anyway, I won't give the entire list, but just for curiosity, I played around and I found these things. And when I talked to Aryeh Cohen, he said, "Oh yes, I found those myself." So, if with some pure thought, I think a lot of people probably found that. So the idea was this is an interesting problem, and it looked like the classification of finite simple groups was coming to an end. So we needed to have some new topics to study. Okay, so we started to classify finite subgroups of exceptional algebraic groups. Now, this is a broad category, but we restricted ourselves mostly to quasi-simple finite groups. And that means a group F which is finite. F is the commutator subgroup of itself, it's perfect. And F mod the center is simple. So our question is how to look at the quasi-simple finite groups, which are in principle known because of the classification of finite simple groups, and ask which of them can embed in one of the exceptional algebraic groups. Okay. And it's pretty easy to see that not every finite simple group can embed.
The quotient model of the center is simple.
Yeah, but F or F prime?
No, F is equal to F prime.
F is equal to
It's perfect.
Sorry.
Okay, let me give an example. SL25 and F mod the center is the alternating group. Okay.
Sorry, what is the notation? 3E6?
Yes, E6, the simply connected form has a center of order 3.
So
And I write this it's just my reminder that this is the simply connected version.
For
Okay.
people in the finite group theory, E6 is the adjoint.
Yeah. There are many cultural battles that we face when I give a general
For
talk.
us, it's simply connected, but for them, it's the adjoint.
Okay. Okay, well, I hoped you enjoyed this story from my youth. It's not up to Gogol standards, but, well, okay. All right, let's see. No, I think I should do these in a certain order, but it's too late now. I'm not going to read off my notes, but I made some. Yeah. So during the period 1984 to 2002, I worked with Aryeh Cohen, and then Alex Reba on various aspects of this problem. And there were other people who appeared for short periods of time, but these are my main collaborators. So we have a list We got a list of candidates, and we were able to eliminate almost everything. I think everything on our list eventually did appear in some form, and we got a more precise list, and the list I call QE. That's the set of F such that F is quasi-simple and F embeds in an exceptional complex algebraic group. So this list is exact. And let me just indicate some of the basic questions that arise. Let curly A be the set of S, where S is finite. Oh, this is finite. Simple and some central extension of S embeds in an exceptional group over the complex numbers. So, in other words, if you just take everything in this set and take all the central quotients, you just get this set of simple groups. These are simple groups. So we, actually with R.E.A. Cohen, the list that we had, all the candidates turned out to be really, all of them survived. They could not be removed. But there were a lot of question marks in our table. And if S is in curly A, and S tilde is a central extension, then S tilde may not be in QE. There's an example. I forgot the smallest example, but we spent some time with S equals PSL34. And there are two extensions that look like this. Perfect. And one of them embeds in E8 and the other does not embed in E8. That's not obvious. I mean, it's really kind of technical stuff. But we got the exact set of isomorphism types in here that correspond to the simple groups here. So.
Sorry, those examples that you had before, they were not central extensions.
Which one are you pointing to, please?
You know, this 3-cube SL33, that's not a central extension.
It is not, and I didn't claim it was a quasi-simple group. It's just an example of an unusual subgroup that's the normalizer of an elementary abelian group that's not in a torus. So.
Okay, so but here we are looking at central extensions.
That's right. We are limiting ourselves to that question. Yes. Okay. And well, you can imagine the list is very long. There are many small dimensional linear groups, orthogonal groups, and so forth, and it stops after dimension 8 or so. What is in here? This has alternating group of degree n for n less than or equal to, I think it's 17, something like that. It's a little surprising. It has M12, the Matthew group, but M12 is not in QE. Why? It's because the double cover of M12 is in QE. Again, it's not obvious, but it's sort of a delicate thing. For example, when you look at the there's a big group of type D. Where is it?
Is it not because 17 is 18 minus 1?
Well, let me think. No, it's because 17 minus 1 equals 16.
Okay.
And the reason 16 is important is 16 is 2 times the rank of D8.
Okay.
But the form of the D8 group is a half spin group. It's not the orthogonal group. So when you put in a big alternating group, you have to deal with the spin version of the alternating group.
Half spin. Okay.
That has, well, the alternating group has a double cover, so I don't need an additional word. But the half spin form of D8 can accommodate the double cover of alternating 17, but not the simple group, alternating 17. Okay. I have to erase. Does this work? Yes? Oh wait, no. I have to use high-tech stuff here, right? So goodbye to my story from my youth.
You see, it's so much more efficient, this thing.
It is. It is. Let me. So please ask me questions if something's on your mind. I didn't think of that. That's good. Okay.
You can write here.
Okay, good. Thank you. Okay, now. Oh, it's,
Oh, you can write. You can already write.
okay, good. Okay, now. Conjugacy questions. Suppose we've got F a finite group and G an algebraic group. We look at the set HOM, FG, and which is infinite, of course. Well, it could be zero, but we're interested in looking at homomorphisms up to conjugation in G. And this is finite set. Okay, so for every group in the set QE and G exceptional, would like to know this finite set. Well, or at least it's the cardinality. And there are lots and lots of cases, and we know the answer in a nice number of cases, but it's not clear. It's not close to the complete story. So let's take a few cases. So G is some exceptional group. H, Coxeter number. There was an observation of Costant that 2h plus 1 is a prime power. For G, a simple algebraic group, that this isn't true usually, but it's true for the exceptional groups. And it seems that PSL2 of 2h plus 1 embeds into G. Now think about G2, F4, E6, E7, and E8. For the smaller cases, this was known to be true. Okay, so known for, how do I say it in a clever way, H less than or equal to 12. For E7, H is equal to 18. And for E8, H is 30. And Reba and Kleidman and Meyer-Frankenfeld proved that this is yes for H equals 18. That's the E7 case. So PSL 237 embeds in E7. And their proof is short, and it's actually done with pure group theory. It's not a computational result. Now for H equals 30, E8.
You say it's pure? You said it's pure thought? This result?
Pure group theory. They use the classification of simple groups, some very strong techniques, but it's not a computational theorem. Okay. For H is 30, that's the E8 case. The question then is PSL 261 contained in E8. And the answer is yes. And it's due to the work of Cohen, and myself, and someone named Bert Lisser. I have not met Mr. Lisser. And we set up a tremendous theory that sort of pinpoints where to look, and some computation was necessary. So I'm going to say, okay, this uses computer, and something that came a little bit later was the fact that the embedding is essentially unique, so this number would be 1 in that case. Okay, so how about these proofs? Computational proof of embeddings. Let me say a word about how these things are done. If K is an algebraically closed field of characteristic P bigger than 0, and if P is relatively prime to the order of F, our finite group, then these numbers are the same. Oh, sorry, mon G.
You mean the conjugacy classes?
Yes, the embedding or homomorphisms up to conjugacy. This is very familiar to people who do representation theory of finite groups. You can take a representation over the complex numbers, write it over a finitely generated algebra over the prime field, and then you take, in that algebra, you take primes and then reduce, and you get embeddings into positive characteristic general linear groups. When the characteristic of this is relatively prime to the order of the group, you have a one-to-one correspondence. And when it does divide the order, there's some degeneracy, and it would take a whole course to explain all of that. But that theory, which does not require any kind of fancy algebraic geometry, corresponds to this. It's an exact analog. Okay. So for computations, it may be good to work over a field of a positive characteristic which doesn't divide the order of the group. If you can settle the question there, then the answer is transferred to the complex case.
So you just take a finite splitting field or something like that?
Yes, but for ordinary representations, I know how to define splitting field. I'm not sure quite how to define it for this more general case. But
the idea is this.
Yes, it's the idea. So let's be very concrete. Let's take this. For PSL 261, we used the finite field O. I don't want you to erase, so let me put bars. We used K without a bar. The integers mod, let me get this right. I need 30th roots of unity, and I need 60 first roots of unity. What's that? That's 18, 30, and then I add 1. So that's a prime. I'll show you the kind of calculations we need, but this gives me the roots of unity that are appropriate for the calculation. So, okay. Okay, now what exactly do we calculate to do this? Okay, so let's suppose we wish to find a homomorphism from F to G over some field. We use a presentation. I'll call it pi for F. So that's a set of generators and relations. And if I find elements in here which satisfy that presentation, then I have a homomorphism. And if F is simple, it's an embedding as long as I can see that one of these elements is not the identity. Okay, so that's pretty easy. Okay, so how do we do this? Let's say F has generators. Well, let's say it has a subgroup S and an element X outside S, so that F is generated by S and this additional element. Now S is supposed to be something convenient or easy to work with. It's typical that we can find a big piece of our group F inside here. For example, in the normalizer of a torus, maybe. So we can get these elements to correspond to elements of this. But what should the choice of X be? Well, that's not so obvious. We want every defining word W in the presentation to satisfy W of, you put in the elements of S, and then you put X. Oh, I'm sorry, I'm saying this very badly. Excuse me. I think I better look at my notes. I want to word this the right way. I think I'm getting ahead of myself. Let me just say, we get a monomorphism phi from S to G of K. And this part is fairly easy, and we seek an element Y in K. So that there exists a homomorphism phi from F to G of K, which extends, let me call it phi hat, which extends phi and takes X to Y. Okay, so in other words, elements of G of K that satisfy the presentation. Okay, now let me do the magic operation.
Y is from the group of points. G of K, what is? Y is there is from J of K.
Yes, Y, yes, thank you. Thank you, G of K. Yes. Okay, now some analysis. Limits, choice of Y to a certain set. Let's call it C. C for candidates. So if there is a Y, it's got to be in here. Okay, and then how to find a good Y? Well, take a word. Okay. Suppose there's a word in the presentation, and it factorizes. Into shorter words, and let's suppose x appears, let's say n times in this word. So you're solving a degree n equation, an unknown, but it occurs n minus 1 times in W2 and once in W1. And suppose also that there exists a vector in L, the Lie algebra, so that if we take W of plugging in phi of s and y applied to v, that's W1 phi of s y, W2 phi of s y v. Now suppose sometimes you can arrange it so that this piece, even though you don't know exactly what it is, leaves v fixed. Then what you have is a demand. This word is supposed to be the identity, right? That's what you want. So your condition then is simply a linear condition in the parameters that describe y instead of degree n. Okay, so this gives an equation which is linear in y. Now, in the case of PSL 261 and certain other cases, C is a coset of a torus. So you can take an easy-looking coset representative and then use parameters to describe the torus. And when you write out the equations, this piece goes away, and you're left with linear equations in the parameters. There's no reason for that system to have a solution unless there actually is an embedding. So if there is an embedding, this will produce at least one candidate. That doesn't mean that it works. Then you have to take that candidate and plug it into all the words in the presentation and see if that works. And it does work in a lot of cases. Okay.
And this is done by computer.
Yes, this part was done by computer. Yes. And so this worked for PSL 261 and some other cases.
Now I understand why Ari was so worried about the structure constants of E8. And he and Lisa and someone else have published a paper on the structure constants.
Yes, yeah, I have one paper with these other two, but then they wanted to know whether, and then we proved that PSL 261 is unique, but then the question is, if you don't use this trick, is it still true that there's a unique solution? And the answer is yes, it's still true. So I think that was their second paper. Mm-hmm. I don't know the third author in that case. Okay.
Does the Weil group of E8 contain this group or not?
No. The Weil group of E8 looks like a double cover of O plus 8, 2, and the order is 2 to the 14, 3 to the 5th, 5 squared, 7, and times 7. There's no 61.
It stops at 7?
Yes. The Weil group acts on Q to the 8th. So if you think of cyclotomic polynomials, then yeah.
The Lie algebra of E8,
Yes?
and it decomposes in some small number of pieces.
Yes.
Some interest or no?
So the Lie algebra E8 as a module for PSL 261 is a sum of 4 pieces of degree 62. Was this your question? Just as an abstract representation theory question, yes. Yeah. So.
That doesn't help me, it's not relevant.
Well, I'm skipping over some details. Let me just add a few more details. Okay, so let's start at a more basic stage. So we consider F a finite group and possible homomorphisms from F to G, some algebraic group. Okay, the way we start usually is this. If F has an element of order n, we find all elements of G of order n up to conjugacy, because that will tell you possible images of the homomorphism, if there is a homomorphism on elements of order n. And there's a machine for doing this. We used a version due to Victor Katz, and there are older ones, but can be done with labels of extended Dinkin diagram. So I'll explain this in some detail if you want, because I've done it quite a few times. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. Whoops, what's the matter with me? 6, 4, 2, 3. Those are the weights in the E8 case. Suppose you want an element of order 31. Then what you do is assign integers to each position, and then you take the dot product of these two integer vectors. That should be 31. And this set of integers should generate the unit ideal in the ring of integers. If you do that in all possible ways, you find all elements of order 31. Now, for our case, the element of order 31 would be given by the labeling. I do hope that adds up to 31. 6, 10, 15, 25, 27, plus 3 is 30. Whoops, what's wrong? Something's wrong. Maybe this is a 2. Anyway, there's a unique labeling. Because we know enough about PSL 261.
1. It should be 1.
It should be 1, okay. So my brain's no good. And then, so we would do this for each element, elements of each order in, for example, PSL 261, and that narrows the possibilities quite a bit. So we do that. Then we want for each M and each element X in F, we want this to be in the conjugacy class of this. In other words, we know this by the labeling. you take it to the nth power and you get some other element of finite order. You have to figure out what the labeling is. And sorry. That's another set of conditions. And at that point, things are fairly tight. There's no theorem that says that has to be the case. But the fact that PSL 261 doesn't lie in a smaller group of Lie type, it can't lie in a proper algebraic, positive dimensional algebraic subgroup of E8. There are a lot of reasons to eliminate candidates. So very quickly we get what the character looks like, the trace, and we get this decomposition that is actually pretty routine. Okay, it is also a fact that PGL, this is PSL, 2H plus 1 embeds in G. G is the same as here. It's a particular exceptional Lie group. H is the Coxeter number. So if G is G2, F4, E6, E7, E8, then H plus 1, 2H plus 1. What is this? 6, 12, 12, 18, 30, 7, 13, 13, 19, 31. Okay. Oops. I don't know who observed this first, but Sayre certainly told me about it, and he wrote a paper after our PSL 261 theorem, where he gave a theoretical proof of existence of an embedding of PSL 261 in E8, and actually several of these other cases. Of PSL 261 in E8. It's very nice. And I've forgotten exactly what he proved in this case, but this case was done by Reba and myself. So here's something that's universally true amongst the exceptional groups. Now, if you take classical groups, these numbers aren't necessarily prime powers, and the statements could be kind of messy. I don't know exactly what to say about that, but the pattern probably extends in some way.
Yeah, but in classical groups, you know essentially representations, and you know when these representations are symplectic or orthogonal.
Yeah, but the question is whether you have this nice pattern.
Yeah, but I mean, in principle, you could solve it for any group.
Yeah, probably so, yeah. Okay, and then there are some other numbers, and I forgot how these are defined. They're Springer invariants. Does anyone know about these? Well, we looked them up, and they led us to prove embeddings of PSL 241 and PSL 249 in E8. And these are not connected to the Coxeter number in a very simple way. So, do you know these Springer invariants?
Springer, you mean Tony Springer?
Yeah. I'm sorry, I just don't remember the definition. But Sayre said, oh, look at these numbers, and sure enough, we got that. And oh yeah, we also proved PSL 232 is in E8, and Suzuki 8 is in E8. And maybe my favorite theorem, or maybe after PSL 261, that was the first one, but PSU 38 is in E7. And it's unique. And this was the groups PSL2. Their subgroups are very thin, mostly sort of cyclic groups or dihedral, and you can't play with subgroups of those against themselves in a very interesting way. But this has subgroups, an elementary abelian group of order 2 to the 8, and a very complicated CeLO 2 group. So it was possible to use the group theory to base a lot of analysis. And this proof was done almost without computers. Alex Reba is maybe the greatest in the world at computational group theory, and he likes to eliminate the use of computers and really trim down very carefully what you need to do. And he's really a fantastic person to work with.
Is there a first indication that this may be sitting there?
Is there?
How would one guess it might be?
I can tell you that.
You mean about 41, 49? PSU 38.
Yes. Well, I like that case very much.
There must be a guess that it may be there. And
Yes.
we'll try to prove it.
Yes, there is.
So maybe a large subgroup is already contained there.
Okay, take PSU 38 and look at the character table. And we find this number as the degree of an irreducible character. It's an irreducible degree. Okay, so let V be such a module. All right, so my typical finite group is called F in this lecture. Okay, we compute. This is just straight calculation off the character table. We compute the dimension of HOM, exterior square of V to V. The invariance under F is 1. That means there's an algebra structure which is alternating. But you have to prove the Jacobi identity. Now the Jacobi, you know what the Jacobi identity looks like. It's alternating in the 3 variables. And when you substitute 3 elements from the Lie algebra, you get an element of the Lie algebra. So you have a linear map from the exterior cube to V. If this is 0, then the formal expression for the Jacobi identity is 0. But unfortunately, it's not 0, which doesn't mean that there isn't a Lie algebra, but it means it's not a cheap proof. You have to work. Oh, and by the way, if you do this, take this group. And V equals 3-dimensional irreducible. There are 2 of them, so pick either one. Then the same calculation, Hom F lambda squared V is 0. Hom F lambda cubed V equals 0. That proves
is equal to C. The first one is C.
Oh, sorry. C, yeah, dimension is 1. That proves that there's a unique invariant Lie algebra structure under the action of this group, and therefore this group embeds into the automorphism group of that Lie algebra. That just says the icosahedral group is contained in PSL2. Everybody knows that, so big deal. But anyway, it's nice that this gives an idea, but it doesn't quite work here. But this says, you know...
If this sits inside the Lie algebra, then it should have happened, no? Or no? Because PSU 38 is sitting inside E7 and E7...
Oh, well, yeah, but if you, after our theorem, you know that that's true. But when you start, you asked me why did we suspect that this was true.
Okay.
So you don't have this theorem, but you just look at some numbers and then you say, well, this suggests that that's a Lie algebra. But there's no simple proof as far as I know. Maybe you could play with it.
Eventually this is 0.
No. It just means the Jacobi identity does not give a non-zero.
It's not forced on you.
That's right.
It may be true, but it's not forced.
That's right. That's exactly right. So that was all the work to finally figure it out. And then finally, in the end...
But won't you say this is more algebra than group theory, which is hard? This looks like you have a Hom space, which is one-dimensional. With hard work, you can know what that Hom space is. And then you can try to calculate whether with that Hom space, the corresponding Jacobi identity is true or not true.
Well, we don't determine what this homomorphism is. We don't know. All we know is that I think it's one-dimensional. Yeah, that's just a calculation with characters. But you don't know what a representative of that is. There's no obvious map. Okay. In the end, we verified a presentation for PSU 38. In E7. And I think the group is slightly larger than that. There's some outer automorphisms, but I forget exactly. Okay, so we found elements in E7, and we had to look to search a set of candidates by computer to find appropriate elements that satisfied the presentation. But that was the only use of computer. Everything was completely done by hand. So small frustration. Did I answer your question? Okay.
Actually, you could probably, well, it's easy to see that this representation is symplectic, yes? After which you have to check that it preserves the quoted form over C.
You're talking about PSU 38?
Yes. This representation is contained in the symplectic group.
No, this is contained in the orthogonal group because of the killing form. It's got a 56-dimensional module, and there it's symplectic.
56, yes, right.
And we use...
On the algebra, yes.
Yeah.
Right.
Yeah, and we worked modulo a big prime.
I'm sorry, I was confused.
Yeah, we work modulo a big prime, and in the article we publish a 56 by 56 matrix. It just fits on the page. So.
Right. This one is a problem.
Yeah, there are several things I can talk about. Let me mention. Maps from alternating groups of degree n and their coverings and their central extensions. To exceptional groups. When n is at most 4, these are solvable groups and it's easy to work out. And my student Darren Fry, I think his thesis was 1995, seems like yesterday. He took the case n equals 5, so he was looking at embeddings of alternating group of degree 5 and its double cover SL25 in exceptional groups. And so there are 5 exceptional groups. So for in E8, I got conjugacy classes for all embeddings of the alternating group of degree 5, with one exception. And this was really pretty difficult situation. That's where the fixed point subalgebra on the Lie algebra of type E8 is 0. You see, the fixed points, if you take embed some finite group into the Lie group E8, you can take the fixed point subalgebra and study it that way. And if it's not 0, then this group will be in the centralizer of the Lie group associated to that subalgebra. So in a sense, you can work by induction. You're in a smaller rank, smaller dimensional Lie group. Okay, well here you can't do any induction. It stops, right, just like that. So what to do? Well, eventually George Lustig got interested in this, and he followed an outline of Serre. And there was a lot of character computation. And Lustig is a master at the characters of the Chevrolet groups over finite fields, and finally got the uniqueness of a fixed point free embedding of the alternating group of degree 5 in E8 of C. So the question mark in Fry's thesis at this point can be erased, and you write one conjugacy class. So, and this was not trivial, and it's clear you need a new technique. You just can't play the usual game with subsets of a Lie group and their centralizers. Okay, and since then, most questions, oops. About, I'll call it star here. Have been answered. And he recently told me that he co-authored a long paper with someone in theoretical physics. This person needed very detailed knowledge about alternating groups of degree 5 and SL25 contained in E8. And so their paper is over 70 pages long, and they disagree about one case. They couldn't resolve their disagreement. So there remains that question mark. But anyway, there's a lot of progress that's been made on that.
Robert, before you raise this 41 and 49,
Yes.
What occurred to me is that it might be related to the orthogonal decompositions of the Lie algebra of type E8. You know that E8 is the direct sum of 31 copies of
Yes.
Cartan subalgebra.
Yes, yes.
Orthogonal with respect to. Have you used this, or have you
No.
tried to establish?
No,
connection?
that doesn't apply to this, to these cases, no.
So it's just a coincidence, the numbers. I mean,
Well, the first example of, say, Lie algebra of type 8 is a direct sum of 31 Cartan subalgebras. This was associated to a finite subgroup. That has its rather complicated form. Okay, imagine a normal subgroup of order 2 to the 15. The nilpotence class is 2, and the quotient by that normal subgroup is GL5 over the field of 2 elements. And it's not split. There's no subgroup like this in E8. So it's a rather complicated thing. So this is what is associated to the first example of.
this is Thompson, or
Well,
after Castrikin and Tiet, Castrikin, Tiet? Who's that?
well, it was found by Thomson, and I'm aware of the work of Castrikin and Tiet, but I do not know the years, and I don't know which came first.
Yeah, okay.
I just don't know that. And this group contains a non-split extension. It's not obvious by looking at it, but this contains a subgroup like this. If you intersect this subgroup with this normal subgroup, then you get this group of order 2 to the 5th. And this is non-split, and it was named after the person who first discovered it, Ulrich Dempfolf. Now, if you're asking me about other examples of this, I'm sorry, I don't know. This is the one, the first one.
So you think there is no connection?
I don't think so.
But 8 is sort of occurs prominently there. You know, it's 5 times 8 plus 1.
Yeah, I know. There are too many coincidences in finite group theory, just.
There are no coincidences. It's all related.
Okay, time to erase at least part of this. I'll say more about alternating groups.
Just a curiosity, this non-split extension is something of recent origin?
No, it comes from the mid-1970s, so it's about 45 years old.
Still, that would be counted as recent, meaning given that such a simple and...
It's not obvious, yeah. It's not obvious that such an extension exists. He proved that
It's an extension of z mod 2 to the power 5 by gn.
Yeah, suppose you have a short exact sequence. Where this is the natural module for that, then it splits if and only if n is not equal to 3, 4, or 5. And the lower cases have an interesting history. This goes back at least to Coxeter. Oh, you remember that group of order 8 in G2 that I mentioned at the beginning of the lecture? Its normalizer is an extension. 2 cubed to the normalizer, GL32. That's not split. That goes back to at least the early 1940s. And for n equals 4, Norman Blackburn wrote a proof about 1970. And in the mid-70s, Ulrich Dempfwolf did this case. And he proved the general result. And the dimension of the second cohomology group is 1 when it's not 0. Okay. And I'm not quite sure how to word this, but Darren Fry wrote to me that almost all embeddings of alternating group of degree n in an exceptional group are known up to conjugacy. We would like to say that for SL25, but there's some arguments already, so it's not quite that good. I really mean there's just 1 or 2 cases left, and the hard case that has just been settled is alternating group of degree 6 in F4. The number of conjugacy classes of embeddings has been settled. That's very recent, and it seems to be very technical and very difficult. So, okay, that's Reba and Fry. And I should also mention that in our papers, we settle the number of conjugacy classes of embeddings, I think, in almost every case. But if you look at that whole list, most of the entries don't have an answer, but maybe about 1/3 of them do at this point. Okay. Any questions about this? Okay. Let me talk about conjugacy within G2. And so here's the problem. Given 2 sets, well, S and T, okay, so, and I'm working over the complex numbers. When is there an element of G2 so that S to the G equals T. And I hope you don't mind my notation. This is G inverse SG. Okay. Well, you need some kind of hypotheses. And the theorem that I found and this is also by Michael Larson. We proved this independently with different methods, and we each didn't know that the other person was working on it. So I think it was pretty interesting.
Larson?
Larson, L-A-R-S-E-N. At Indiana University. Okay, S and T in G2. And G2 is contained in B3 of C. That is the it's the special orthogonal group of dimension 7, right? There's a natural 7-dimensional representation of G2. Okay. Then if there exists a B in B3 of C, so that B conjugates S to T, then there exists a G in G2, and C in the centralizer in B3 of S, so that B factorizes as C times G. So if S and T are conjugate in the larger group B3, it follows that they're conjugate in G2. But even more than that, the precise map, the set map that takes S to T is realized. I don't mean, it's not just the whole set, S goes to the set T, but the exact function is captured by conjugating by an element of G2. And a corollary of this, now these are subsets. There's no structure, just subsets. Okay, a corollary is if S and T are finite groups, finite subgroups of G2, then they are conjugate in G2 if and only if their 7-dimensional characters are equal. Okay, so we've got finite groups, so we have more information. There is structure, there are character tables. You can look at their character tables and find the appropriate 7-dimensional character, and if they're equal, then they're conjugate in G2. So that was something I was very surprised about. Sarah kept asking me whether that was true, so I didn't think it was true, and I couldn't find a counterexample, and so I was able to prove this, and then I learned that Michael Larson used completely different methods and proved this. But I think this is kind of interesting. You don't need them to be groups, just subsets.
There you assume, what do you assume from the character table? Actually, you S and T are just finite groups. You do not assume that they are the same order? Or
Isomorphic.
Isomorphic.
Yeah, so there's at least one way of identifying their character tables, and then if you can, yeah. Okay.
Is it possible to say what is the most crucial property of G2 inside SO7 which is put to use in this theorem? Maybe by you and by Michael? Maybe
Well, Michael Larson, I don't remember his proof well enough to give a spontaneous explanation, but
one has this embedding of G2 inside SO7.
yes,
And one wants to prove that conjugacy inside the layer group is same as conjugacy in this model.
yes.
So there must be some property of the embedding which is crucial for the proof to happen. Of course, one thing is that for elements it should be true that two elements of G2 are conjugate if and only if they are conjugate in SO7.
Yeah,
So this is what is called element-wise conjugation.
yes, yeah.
So whether that is true,
There are plenty of examples of two finite groups in a Lie group, and element-wise, the elements all have the same trace, or even conjugate, but the groups aren't conjugate.
right? So there is something
Yes.
more tight here.
Yeah,
and
that's
there
right.
must be first reflection of what is better.
Okay.
This is
All right.
because G2 is twisted form of B3 or something?
No, it's not a twisted form of B3, no.
Well, it is actually.
Well, this is rank 2 and B3 has rank 3.
So it's, I mean, well, it's twisting of B3, sorry.
What do you mean G2 is a twisted form of?
Well, not twisted form, it's a twisting of, folding of B3.
Well, it's
in the same sense as it is a folding of
Well,
D4.
it is easy to visualize it by embedding them both in D4, no?
In D4. D4 is, B3 is a twisted form, well, not twisted, folded form of D4. And G2 is when you sort of continue this folding.
Triality D4.
Yeah, if you take the fixed points of the triality, you get
but
G2.
B3 is in between. You just identify
I
two
know.
tails and then you proceed and you identify the short root with the long one.
Okay, well, let me,
So, okay, let's say, can we extend this statement to D4? I mean, if two subsets are conjugate inside D4 of C, then what happens?
Must be true. Maybe simpler, as Vavilov says, maybe that is more general.
Exactly.
The diagram automorphism, the fixed
Exactly.
points, the conjugacy in the fixed points and conjugacy in the bigger group are the same, must be related to more classical mathematics, whereas this is little maybe subtler. No? I think this is a more difficult theorem.
Okay,
Yeah,
so you
yeah.
know, about D4 there is no...
I have no statement about D4. No statement. Okay, let me tell you my viewpoint. So my idea is this is E8 and this is G2, isomorphic, and this is F4. So you can imagine all those hypotheses taking place in here, but in the context of E8. Now, if you have a subset, then the centralizer of S contains F. Sorry, the centralizer in E8. Now here I'm certainly concerned about the centralizer in G2, but put that out of your mind right now. And it turns out we can classify possibilities for how F embeds in the connected component. Sorry. Okay, this is an algebraic subgroup, so it has a connected component of the identity, finite index, so it's a product of, well, there could be a radical, I guess, but I mean, S has no structure, so I don't say that this is semi-simple. All right, anyway, there's a connected component of the identity, and F4 is pretty big, so actually there aren't that many possibilities. I mean, 3, 4, or 5 maybe. So you can kind of control what happens with S and conjugation by looking at what happens here. And it turns out, so it turns out given that S and T are conjugate in B3. Now what's B3? Well, it's this means a subgroup B of E which centralizes some B4 subgroup of F. So that hypothesis means you can locate a B inside E where that conjugation takes place, and you can look at what that conjugation does to this. And there's some, I'm skipping the details, but a short discussion leads you to that conclusion. Okay. Then to okay, and what's G? G is the element of B that satisfies this. Okay. I'm really skipping a lot of details, but that's basically what happens. So you get some...
G2 is contained inside B3 and centralizer of B3 is?
Well, centralizer of B3, the connected component is a B4. If you think of D8 and you take the B viewpoint, think of a 16-dimensional vector space and divide it into a sum of odd-dimensional subspaces, you get a product of Bs. Yeah. Okay. All right, I'm skipping things a little bit. Okay, now there is an analog of that theorem that says let F4 of C be contained in...
Excuse me, once again, sorry, but this B4 is contained in
F4.
In F4. So
yes.
I mean, there is another G2 contained in F4 because.
Yes, but I don't have to. I don't have to refer to it.
But if that G2 that you have there is not the one in F4, then
It's not in F4. There's a direct product of groups.
well, there is another G2 inside F4, so
Yes.
maybe that's a source of confusion. So because your centralizer for some reason, so it's a centralizer. I mean, the whole F4 is the centralizer of this G2, right?
Okay, this B is contained in F4. Now look at the centralizer in E of B. The connected component of that is a B3 subgroup.
The B is B3. Or which B? What is B?
B is an F4. B is B. Oh.
I mean, if you stick with that G2 that you have written on the blackboard, then its centralizer is at least F4, right?
It is.
But you just said that the centralizer is B4.
No. I wrote something wrong here. Excuse me. B3 is a subgroup B defined as follows. There exists a B in F4, and this is what I mean by B3. G2 commutes with F4, okay? Then you drop to a subgroup in here called B4. The centralizer of that is a B3 that contains G.
G2.
Well, I call it G, but yeah, G2.
So the centralizer of B4 is B3.
Yes.
Well, that's not so easy to visualize. We have to draw the Lincoln diagrams.
Well, already in D4. In D8.
If you just think in D8, think of the 16-dimensional module.
The rank should be 8, no? Should be 4, not 3, no?
No,
So
no.
There is a total component in the centralizer?
No?
Wait.
If you have a semi-simple subgroup, the centralizer, its dimension, its rank plus the rank of the centralizer is not necessarily the full
It's
rank.
not a regular.
The centralizer of D4 is D4, but it's B4 it shouldn't be.
It's B3, yeah.
But you are going to say that one can see it using D8 inside D8?
I'm saying if you take a natural B4 inside D8, okay, that's a 9-dimensional orthogonal group inside a 16-dimensional orthogonal group. The centralizer will be a natural 7-dimensional orthogonal group. That's why I was suggesting the centralizer of B4 is a copy of B3. Okay. Okay. All right, so let me go to the next theorem. This is the simply connected E6. And we have ST subsets of F4 of C. If G is in the bigger group and G conjugates S to T, then there is a C in the centralizer in 3E6 of C of S and a Y in F4 of C, so that G is equal to CY. So it's a strong kind of conjugacy. Okay, so in other words, fusion of subsets inside F4 is controlled, strongly controlled. Fusion by within the group triple cover of E6 is strongly controlled by F4. That's the analog of this result. And the proof, the idea is to reverse
Yeah, so this is related to folding.
It's exactly the folding.
Yeah.
Okay, reverse the role of G and F. So the arguments I made with G involve taking subsets and looking at their centralizers in E8. That's a group that contains F. Okay, well, if I start with a subset of F, then the centralizer will contain this G, copy of G2, and you can classify them well enough to do an analog of this. And I'd never heard of this theorem before. I proved it. It was just a formal game. You know, I tried to copy the idea I used for G2, and this is what came out. Okay.
You know, I was asking, there is the first observation which one needs to make, that elements in the subgroup which become conjugate in the bigger group
Yes.
are already conjugate in the smaller group. I think that will be a generality for folding. I think whenever there is this diagram automorphism and the fixed points, then the fixed point has this property that two elements are conjugate in the smaller group if and only if they are conjugate in the bigger group.
Okay.
And then maybe this is the better theorem.
The folding is a centralizer of certain automorphism, certain.
So it's a triviality.
No, I'm not claiming that, but I'm saying that folding should be viewed also as a centralizer of something.
Yeah, of the outer automorphism.
So maybe that helps.
Yes.
Okay.
So excuse me, so here subsets are just any finite subsets or?
Not even finite, just subsets. Now, let me make one comment here. Suppose they happen to be finite groups. Here you can take advantage of character theory and get this conclusion that they're conjugate. But here, suppose these are subgroups. Well, the analogous procedure would be to consider what it means for them to be conjugate here. But there's no easy criterion. There it's character theory. And here there's nothing. So if you're already busy classifying finite subgroups of all the exceptional groups, you may have some information to use. But there's not an analog of a character theory argument, as far as I know. So this has been used by other authors, so I did somebody some good. Okay, let me see. When am I supposed to stop?
Well, it's up to you.
Okay.
Would we like to continue next week or something?
Well,
I can.
if you can continue.
We have
well,
at least
that
25 more minutes.
Huh?
I think we have at least 25 more minutes.
Oh, okay. Well, then I can.
It's already an hour, maybe next week.
Well, it's up to you, actually. But would like to do next week 2 days in a row on Wednesday and on Thursday. I mean, on Wednesday continue the seminar talk and on Thursday the colloquium talk. Or otherwise, we can.
Well, let me go 25 more minutes.
Okay.
Or maybe just 15. I have a few more things to say. Okay, one is.
Can I ask you a question?
Please.
You know, I was just wondering, I mean, the obvious thing to understand if two subgroups of a group are conjugate is whether for all linear representations of the bigger group, these two subgroups are conjugating by the corresponding GL.
Yes?
So that will correspond to the element lines. Okay. So
Yeah, that's right.
So that is
Yeah. That gives you equivalence of characters, and we know what that means in GLN. Okay. I had two short topics. One is called complexity, And the idea is that I have a result for E8, which might be generalized. And I haven't quite figured out how to do it, but I think it's kind of an interesting property. So in E8, this is the Lie group, there are two conjugacy classes of involutions. 2A is the usual notation for 1, and the centralizer, oops, is type A1E7. And in more detail, it's SL2 central product double cover of E7. These factors commute element wise and their intersection is order 2. Okay. And then 2B, the centralizer, has type D8, and it's also known as the half spin group. Okay. So now I consider
Is it possible to say why the nomenclature? 2A to B?
well, I think it follows the style of nomenclature in the Atlas of Finite Groups. And the rule there seems to be when you list the elements of a given order in a finite group, you list them in the order of centralizer size. So this centralizer is bigger than that in the sense that the dimension exceeds the dimension of that. This is 134 and this is 120. So
It's more than 130, it's 130.
well, this is 134.
6.
Oh, sorry.
No,
What's
no,
the
no,
matter?
no, no.
No, you're right. You're right.
6.
And this is 120. Okay. Okay, so I consider elementary abelian two subgroups. Let's see, I can't use E, and I can't use A, and I can't use B, so how about H? And I assign a function, degree let me start again. I define the complexity of H2B, the degree of, what is it called? The characteristic function of this set. Take the conjugacy class 2A. Some of the involutions in here will be 2A and some will be 2B, right? So you take the intersection and you get some subset of H. And this is, and take its characteristic function. You know, it's 1 if you have a 2A for the 2A elements and 0 otherwise. Well, this is a polynomial function. Take...
Degree, you mean the order of the set 2A intersection H?
No, I mean the degree as a polynomial function. This is the characteristic function of this subset of H. Any function on a finite vector space is a polynomial function. Not in a unique way, but it is. So it has a degree, the degree of the least such polynomial, okay? And Lamothe, this degree, a complexity, is less than or equal to 3. That requires examining the elementary abelian subgroups of E8. It's not obvious. And the theorem I have is that H is in a torus if and only if the complexity is less than or equal to 2, and H does not have dimension 5, and all involutions of type 2b. Now, maybe this is not the best way to say it. There exists in E8 a rank 5 elementary abelian 2 group with no 2A involutions. So just accept that for the moment. So except for this case, you take your H. If H has no 2A involutions, the degree is minus infinity. So this inequality is achieved. And if it does have 2A involutions, the complexity is less than or equal to 3. Okay, well, if less than or equal to 2, if and only if it's contained in a torus. So that is the result I have. I thought this was kind of interesting, and I would like to know if there's an analog for other algebraic groups. Probably not, but maybe for some of them. The worst, the villains in this story are the type D groups for some reason. They have many classes of involutions, and the distributions seem to be quite messy. So this is an interesting point, I think.
Perhaps one could classify all elementary abelian 2 groups up to conjugacy in E8.
The maximal ones are known.
That's order 8 and order 9.
Rank 8 and rank 9, yes.
Rank 8 and rank 9.
Yes. Yeah.
But one doesn't know all the conjugacy classes.
I don't think so.
Who was that? Cohen and Seitz or someone? Or was it known before that?
This should
Maximum.
John F. Adams.
John Adams, or
Adams.
J. Frank
Okay,
Adams.
okay.
Yeah. Yeah.
So there is maximal of order rank 8 and maximal of
Yes,
rank 9.
of course. They used this.
Okay.
But this part again makes me think that it's because E8 is generated by 5 root subgroups, long root subgroups.
Oh, really?
Oh, it is.
Okay.
So it's, I think it might be related.
Okay. Let me. Okay, so my last topic is to. Wait, I didn't wipe this off, did I?
I think coordinate sites give it a positive characteristic. They answer the maximal elementary abelian for positive character. Other
2 is the
0,
problem. 2, 3, 5 is the problem. Otherwise,
yeah, exactly. Yes.
but as he said, conjugacy classes are actually away from 2 is in bidirectional with complex numbers.
Yes,
So
I
that's
know,
one.
yeah.
Only characteristic 2
They
is
solve the remaining cases. Yes,
Characteristic
that's what
two.
it is. Right.
Okay. Well, here's my last topic, and that is finite groups and vertex algebras. This topic may not be well known. It would take a whole lecture to give the definition, so I'll just sketch it very briefly. Some graded space. Over the complex numbers. The vertex operator algebra. And the dimension of Vn is finite. And there exists a linear map it's called Y from V to a two-sided power series in a variable z. So when you apply it to an element of V, okay, so the Vn's are endomorphisms of V. And there is a special element called 1, a vacuum, and omega a Virasoro element. And there are quite a few axioms that really need time to discuss. But I can state a theorem quickly. The automorphism group of V is the, oh, sorry.
Is a graded algebra?
I haven't said anything about the algebra, the products yet. Let me do that. For every integer, there is a product on V, and it's like this. A and the nth product, B, is a n of B. This a sub n is an endomorphism, so you can apply it to an element of V. So you have countably infinite set of products on V. So in a very complicated way, it's an algebra. Okay, now an automorphism of V is a linear isometry V to V, which preserves the vacuum element, the Virasoro element, and hence the grading. And all these products. If you have a finite dimensional vector space in an algebra structure, an invertible map is it preserves the product if and only if it satisfies a set of polynomial conditions. So you get an algebraic group that way. And the theorem proved with Chongying Dong and myself. If V is finitely generated, aught V is an algebraic group. Finite dimensional algebraic group. So This is an algebraic group seminar, so of course I wanted to mention that. But moreover, oh, I guess I have to do this again.
This is a generality. B is any finitely generated algebra. It's independent of what went before, or it is after what went before.
I don't know about if V is a finitely generated algebra, but this is a finitely, the set of generators in this case lies in the sum of a finite number of terms here. So the restriction of any automorphism to that finite piece determines the automorphism. So it's a finite dimensional group. Now your question about dropping the grading, I don't know how to answer that. Okay. And now there are nice VOAs, whatever that means. Think about what's a nice Lie algebra. Well, it's finite dimensional, semi-simple. Okay, of course. So there are conditions that are technically very hard to explain. There's called regularity and C2 cofinite and similar things. So you would like the nice Lie algebra theorems to apply to the nice VOAs. You'd like to make some analog. And there is a theory of derivations. And they form a Lie algebra. Any algebra has a Lie algebra of derivations. And if you have an infinite number of products on a given space, you just intersect all those Lie algebras and you get those derivations that preserve all the products. Would like every derivation on V to be inner if V is nice. So what's inner? Well, let me give you the easy case. If dimension of V0 is 1, there are ways to, I'm restricting myself too much here really. You can grade with negative integers and other things. But suppose the dimension of V0 is 1. If A is in the degree 1 part, then this endomorphism, A0, is a derivation. And this is called inner. So I'm simplifying a bit, but this is roughly what it means. So if you assume lots of nice properties for a VOA and try to prove that every derivation is inner, there doesn't seem to be a proof. And my co-author is a big expert in VOAs, and he's absolutely stuck. He can't do it. So I think that would be a great contribution to VOA theory if someone could do that. And I think I'm at the end.
Okay. Thank you very, very much for your beautiful talk. Are there any further questions?
What is this algebraic group? Is it something which we already know?
No, I just proved that it's a subgroup of a general linear group on that sum of a finite number of spaces that satisfies a polynomial conditions. That's an algebraic group.
Meaning it could be E6, E7, E8?
Yes, but furthermore, there are nice VOAs. For example, take a root lattice of type ADE. I can make a VOA in a standard way out of a lattice, and the derivations will just be the Lie algebra, and the automorphisms will just be the corresponding algebraic group for that Lie algebra. That's the natural answer that you would guess. But for general VOAs, It's just an algebraic group, if it's finitely generated. If it's not, I guess it's a pro-algebraic group, but I'm not sure.
Int algebraic group or pro-algebraic?
Well, I mean, you can restrict automorphisms to...
So pro-algebraic is yours.
Yeah, if V is not finitely generated, if you take automorphisms, you can restrict them to any partial direct sum. And then that generates a sub-VOA of this. And then if you increase the direct sums, then you get larger sub-VOAs.
It's covariant, so it's int, no?
No, I think it's...
From the full automorphism group to the subgroup of the automorphism which fixes certain part, there is a mapping, so it's a group.
Yeah, I think... Anyway, we didn't prove that, so I'm not sure.
Okay, any further questions?
Okay, this is a lot of material, so I'm happy to talk to anybody who's interested.
This part is related to monster and the moonshine.
In that, well...
They also have VOA.
Yeah, but there are no derivations, and the automorphism group is a finite group, which is an algebraic group, and it's the monster. But derivation theory says nothing.
So, any further questions? Actually, Robert will be here also next week, and next week there will be another talk at the Colloquium concerning sporadic groups, so everyone is invited. And, well, if there are no questions, let's thank the speaker again.